The problem we've been looking at recently is this. Given n plus 1 data points, each of which has an x value and a function value with distinct x values, we want to find a polynomial p of x so that when you evaluate polynomial p at x0, x1 out to xn, for instance, what you get back is the corresponding function value from your data set. We have determined that it's possible to do this in the following way. P of x is the sum k equals 0 to n of the function value times what we've been calling L n comma k of x. This is the product I equals 0 to n, leaving out the factor where I is k, of x minus xi over xk minus xi. We have shown that there is one and only one polynomial of degree n or less that interpolates the data set, and this
We want to
is
figure
it.
out
How to write programs to implement this idea. So I've written a sequence of very small and simple programs, each one of which differs from the previous one only in a small way. We'll start with something very simple and then add features until it's doing what we want it to do. This program is going to have two integer variables, I and n. N will eventually be the largest index in our interpolating data set. I will be a loop counter. Having said implicit none, we declare our integers. We also declare two double precision numbers, x and y. The user is asked what value of n they want to use, and then it is read from the keyboard. For I equals 0 to n, the x value and its corresponding y value, which I'm thinking of as the function value, is read from the keyboard. Then the next one is read, and so on and so forth. Since each one is being overwritten by the successive one, and nothing's being done with them anyway, this program does very little, but it'll help us build our infrastructure. It compiles with no trouble. If I say that n is 3, it's going to want 4 data points, indexes 0 through 3. I'm just making these numbers up. So it read the data correctly, as far as we can see, but as we said, the program did nothing. Next, we change the declaration of the double precision variables x and y to have array indexes that can go from 0 to 100 inclusive. The user is asked what the value of n is once more. If n is larger than 100, then the amount of storage that we have set aside is not big enough. We inform the user and then stop program execution. If that doesn't happen, then for index values 0 through n, we read the x value and the function value, storing them into the corresponding array positions. Then we print out the information that we've read in just to make sure that it was read correctly. So once again, I'll use n equal 3 and made up numbers for the x's and the y's. The n, as reported by the program, is 3, as it should be. Looking at the x numbers as typed in, we had 1, 2, 5, and 7. We have 1, 2, 5, and 7 reported by the program. And we had the y numbers being 3, 8, 2, and 1, which is what we're reporting here. So we should feel confident that this is correct. Next, we're going to add a routine, a function that calculates the Lagrange polynomials. I'm going to call the name of this routine LNK because it makes me think of L subscript n comma k. Logically, I need to only tell it what the scalar x value at which we wish to evaluate this function is, but of course, it needs to know some other things as well. It needs to know the value of n. Obviously, it needs to know the value of k in addition to the x data values and the particular x value at which I want to evaluate it. In a moment, we'll look at the coding of LNK. To check it, I know that if I take polynomial number k and evaluate it at x number I, I'm supposed to get 1 if I and k are the same index, and 0 otherwise. So as a sanity check, I'm going to look at all possible pairs of indexes, k and I. I'm going to print out the k, the I, and what I get when I evaluate polynomial number k at x number I. So in the evaluation, the second index, the second argument to LNK, is which of the Lagrange polynomials I'm evaluating it at. In the main program, the data that makes up my x quantities is stored in a variable called x. The place where I'm going to evaluate polynomial number k will be x number I. When we print this out, we should see several columns of numbers with associated indexes. If the indexes are equal, we should have a 1, and if they're unequal, we should have a 0. The actual function, LNK, the arguments are n, the largest index in the data set, k, which one of the polynomials we're talking about. Within this routine, to keep it straight in my mind, I'm going to call the set of all x numbers from my data set x data, and the thing that I wish to evaluate LNK at will be called x. When you accumulate a running sum, you initialize it to 0 and then add successive terms. When we have a running product, I should initialize it to 1 and then accumulate extra factors. So initially, I set L equal to 1, and then for each data value, I equals 0 to n. If I is not equal to k, I multiply by x minus x data I divided by x data k minus x data I. We'll use n equals 3 as before. In the checking the LNK routine, this is k equals 0. That's what it means for all the integers in the first column to be 0. The second column is the I value, 0, 1, 2, and 3. Observe that when k and I are both 0, we get 1 for an answer, and otherwise we get zeros. Although the 0 is formatted a little strangely. Negative of 0, though, is 0. When the numbers in the first column are all 1, the only time I get a non-zero result in the last column is when the I index is 1. Likewise, when k is 2 and when k is 3. This is a nice sanity check. It gives me some confidence that my L function is working correctly. Everything is similar. I've introduced a new variable called interp. This is going to be the value of the interpolating polynomial. I did this out of laziness so that I wouldn't have to type the array arguments for p over and over again. After we've set everything up, I'm going to do a sanity check on the p function, which we will discuss shortly. The value of the interpolating polynomial for interpolating value xi will be p in x, y, comma, x number I. The n, as always, is the maximal index. X and y are the x and y coordinates of my data set. And as my sanity check, I'm going to evaluate my interpolating polynomial at the x values at which it is supposed to interpolate. When I print out these numbers, the first two columns are literally the data that I read in from the keyboard. The next column is the value that I got when I feed x value number I into the interpolating polynomial. If the work is correct, that should be identical to y number I, except maybe for rounding errors. This last column is just for convenience. It's the difference between the y value from the data set and what comes out of my polynomial. If things are correct, the numbers in the last column should be 0. We have the Lagrange polynomials, and more recently we have a new thing. We have the p function. P is going to be the sum k equals 0 to n of the function value, number k, which I'm calling y data down in this function, multiplied by lnk, evaluated at whatever the x value that I'm interested in is. We'll use n equals 3. So it sees that n was 3. The x values were 1, 5, 8, 9. The y values were 5, 2, 1, and 0. I made a typo during the data entry. I hit return when I didn't mean to, but even so, it was able to read that when x is 8, y should be 1. Doing the sanity check on the function values, the first column are my x numbers, the second column are my y numbers, the third column are what I get when I feed the x numbers into my interpolating polynomial. 5, 5, 2, 2, 1, 1, 0, 0. So naturally, the differences are all 0. This makes me believe that my interpolating polynomial function is acting correctly. Coming up towards the end, in addition to being able to calculate p of x now, I want to take the range of x numbers in my data set, which for convenience I've been ordering smallest to biggest. I want to select a large number of x values within that range, calculate my polynomial, and print out the results and compare it to the data set eventually. So initially, this is the same as in the previous program. Then I ask how many equally spaced x values, and then I read from the keyboard something that I'll call nplot. Nplot actually is going to be the biggest index of my data points that I plot. Assuming that the x's are in increasing order, the width of the entire interval that contains them is x number n minus x number 0. Divide that by the double precision version of nplot. This is the distance between two successive x values that we are going to plot. We're going to display some x and y coordinates on the graph of the interpolating polynomial. For each value of I, 0 to nplot, the x that we are going to feed into the interpolating polynomial will be the smallest of my data points plus I times delta x. So when I is 0, you'll definitely have one of the interpolating x values. When I is equal to n, likewise, but other than that, probably not. We're going to print out the x value at which we're evaluating the interpolating polynomial and the value of the interpolating polynomial. As of now, this will go directly to our screen. We'll have to do something about that. So we'll use 4 data points. So this tells me, again, that I believe my polynomial is being evaluated correctly, since I've checked it against the interpolating x values. But now I'm going to calculate it at other places. So how many equally spaced x values? I'll just say 14. As you can see, at the very beginning when I was 0, This was x0. After a while, you happen to land right on x equal 9, which was one of your interpolating x points, but the rest of them pretty much are not. And at the end, x is 18 and y is -1 was one of your interpolating data points. So we can get many points now on the graph of the interpolating polynomial, not just the data set. If that were all we could do, this wouldn't be worth anything. Putting this out to the screen is not always convenient. So as my last variation on a theme, I want to think about storing this stuff out to a file. So everything up to here was in the previous programs. This is a new thing. I'm going to make a statement that says open, and then an open parentheses, unit equal 9, say, file equals data plot in single quote marks, status equals replace in single quote mark. This is going to open up a file on the disk for writing. If the file already exists, it will be replaced. Instead of print star comma, I'm going to say write 9 comma star, close parentheses, but no comma after that, although some compilers will allow it. This says print, but not to the screen, to file number 9. The asterisk refers to a formatting statement. It's equivalent to the star in print star. We'll talk about that later. What this is going to do is it's going to print all of my x and y data values to a file that I'm going to call data plot. The reason that I want to do this is I'm going to use some software to draw graphs of these things, and the original data that I had an n in it, so I don't want any n, I just want the x's and the y's. So this will create a file that has my x coordinates and y coordinates in it of my data set, but nothing else. I have commented out the print statement where I was telling the user what was going on. I'm going to open unit number 12, file equals polyplot, status equals replace, and then we're going to do the same thing we did in the previous program, except instead of printing it out to the screen, we're going to print it out to unit number 12. After we get done printing to a file, it's good form to close the file. A word on numbers. Some operating systems and compilers reserve certain unit numbers for internal use. So usually you should think of using your own unit numbers, for instance, 9 and 12 here. Generally speaking, if the unit number is larger than about 7, you won't have any difficulties. After this program runs, there should be 2 files in the directory that I'm in right now that were not there before. There should be data plot and polyplot. Once I have those as data files, I can use my favorite graphics program to draw pictures of them. You'll notice that the files that are in the current directory are a.out, 0.f90, 1.f90, 2.f90, 3.f90, and 4 and 5.f90. There is no polyplot or data plot. I've compiled 5.f90. It wants me to tell it the n, which will be 3 again. I'm just making these numbers up. I do want the x's to be in increasing order, though, but other than that, I don't care what the numbers are. The data that we put in, x values are 1, 2, 6, and 12, which is correct. Y values are 4, -5, 0, -12, which is correct. We do our sanity check for our interpolating polynomial, and everything is fine. We're being asked how many equally spaced values to use. So let's say I want to do 123. Now, apparently, nothing happened. Remember, there were previously only the F90 files and a.out in the current directory. But now there's a.out, there's the Fortran files, but also there's data plot there and polyplot there. Those two files were created by the program that we ran. The current time is 2 minutes after 1 on Friday, September 17th. And as you can see, for instance, polyplot was created at 2 minutes after 1 on September 17th. It was just now created. Data plot says it was created 1 minute after 1 on September 17th. So between creating one of these files and the next file, the big hand went past the top. But in any case, these two files were just now created. It's convenient to be able to draw pictures of things. I like a graphics program that has been around since the Stone Age. Feel free to use whatever plotting software you like, but I'm going to use GNU Plot. So if I want to draw the data plot, file, there's not much to it. There's a data point down here. There's one. There's one. And the last one's down in the corner. This is not very impressive because I only have a few dots. I'm going to plot data plot, and not only that, polyplot. And there are a variety of different plotting styles that you can use. I'm going to say with lines. So this is my first data point. There's my second one. There's the third one. And there's the fourth one. The curve that I've drawn is the points on the graph of the interpolating polynomial that I told it to draw when I told it what n plot was. So you should make sure that you have some way or the other of drawing graphs like this. Also, saving the output as some sort of graphics file, which you could then include into your document. If you're using GNU Plot, this is fairly easy to do. So I want to make a PNG file. And I want to save my result in plot.png. And then all I have to do is plot it again. If I go to my window, let's see, September 17th. I forget where I'm at here. I'm in the directory called September 17th. There we are. Plot.png is a PNG file. I could include it in my document, have a nice picture version of everything that's gone on. It's unfortunate that we had technology issues this morning. Hopefully, this will at least somewhat straighten out some of the things that I wanted to talk about. In the meantime, I hope everyone has a good day, even though it's raining. I'll talk to you again soon.